Hello everyone and welcome to the first lecture of Brief Calculus. We're going to jump right into Chapter 2. If you need to review sections from Chapter 1, I highly recommend you do so. That's going to be on a personal basis. Some people might need the review, some people might not. But we're starting in Section 2.1, an introduction to limits. Our goal is going to be to find limits of functions. Now this note page goes through the definition of a limit. We write the limit as x goes to c of f of x equals L, or as f of x goes to L, or f of x goes to L as x goes to c. So we're looking at the functional value f of x getting closer and closer to a real number L whenever x is getting closer and closer to c. And we'll look at some examples here in a minute to kind of solidify what exactly that definition means. We're going to be starting with one-sided limits. That's where we're getting closer and closer from one side or the other. So here you can see we have x goes to c and there's a little negative sign up there, or there's a positive sign. When we have that c to the negative, that means that we're approaching whatever value it is from the left. And when it's positive, we're approaching it from the right. So we're going to be getting closer and closer and closer from one side of our number. Here's our different properties. We can see 8 listed here. The first one is if we take the limit of a constant, our answer is a constant. So as I get closer to 5, my answer is 5. Pretty straightforward. The limit of x as x goes to c is just going to be that value c. So if I'm taking the limit of x and I want x to go to 1, then my limit is going to take me to 1. If I have the limit of one function plus another function, I can split that up. This is a really nice property for adding or subtracting, where I can take the limit of each function individually and then add them or subtract them after I find their values. Number 5, if I have the limit of a constant times a function, I can pull that constant out front. We can see that right here. And then take the limit and just multiply it by the constant at the end. Another good property, number 6, is if I have the product of two functions, I can take the limits of them individually. Same thing with division. I'll be able to take the limit of my numerator separately from the limit of my denominator, as long as my denominator isn't a 0. And then if we have the limit of a root, that could be pulled out front, and I can take the limit of it, and it's the root of the whole thing. So these properties are really nice because it'll make it simpler in most cases to solve them. So now let's get into the meat and potatoes and look at specific examples that will help us understand our definitions and our properties. Here we have the limit of 9x plus 5 as x goes to 2. So just like before, one of our properties told us that we can plug that in. One of my professors always said, okay, do the dumb thing and plug it in. Does the limit exist? Let's do the dumb thing and plug it in. So let's take our 2 and plug it in there. We will have our limit as x goes to 2 is going to be where we plug in 2. So we'll have 9 times 2 plus 5. And I know that 9 times 2 is 18, and 18 plus 5 will just give us 23. And there we go, we found the limit. Okay, let's do another. The limit of 5x as x goes to negative 3. Same thing. As x goes to negative 3, 5 times negative 3 is going to give us negative 15. Simple enough. Next step, the limit of x times 5x plus 7 as x goes to 5. Now remember, this one uses that product property, so we can split it up into two. So we can have limit as x goes to 5 of just x, and the limit as x goes to 5. Oh, that's horrible. Of 5x plus 7. So now we have the limit of x as x goes to 5 is just going to give us a 5. And the limit of 5x plus 7 as x goes to 5 is going to be 5 times 5 plus 7. This is 5 times 25 plus 7, which should give us 160. Okay, here we have a quotient. We can split that up and take the numerator, the limit as x goes to negative 1 of x plus 8, and the denominator, the limit as x goes to negative 1 of x plus 2. So in our numerator, we'll have negative 1 plus 8. In our denominator, negative 1 plus 2. This is going to give us 7 over 1, which is 7. Let me change my color so we can see this last one. Limit of the root of negative 8x plus 1 as x goes to negative 3. So that gives us negative 8 times negative 3 plus 1, which is positive 24 plus 1 under that radical. Square root of 25 is 5. So not too terrible, just applying those properties straight off the bat. Next up, find the value of the following limits given that limit of f of x as x goes to 3 is 5, and the limit of g of x as x goes to 3 is negative 4. So, first one we have is the limit of 7 times f of x as x goes to 3. Now, what do we know? We know that the limit of f of x as x goes to 3 is 5. So using our properties, we can pull that 7 out front. We know limit of f of x as x goes to 3. That one's 5. 7 times 5, 35. Okay, next up, the limit of 3 times f of x minus 2 times g of x as x goes to 3. So, use our properties, we'll split it up. We have the limit of 3 times f of x, so we can pull that 3 out front. F of x as x goes to 3, that's a 5, minus, we'll pull that 2 out front. These are multiplying. And the limit of g of x as x goes to 3 is a negative 4. So we've got 15 plus 8, that's 23. Okay. Next we have the limit of 2 times f of x over 3 times g of x as x goes to 3. So on the top, we can pull the 2 out front. The limit of f of x as x goes to 3 is 5. We can pull the 3 out front, and the limit of g of x as x goes to 3 is negative 4. So 10 over negative 12, that's negative 5 over 6. Final answer. Okay, now we've got kind of a piecewise function here. Let f of x be x cubed plus 3 if x is less than 1, and 3x plus 1 if x is greater than or equal to 1. Now we'll find all these limits. So we see again that plus and that minus happening. That tells us just look at it either from the left or from the right only. And it's very handy in these piecewise functions because it's 2 functions coming together. We have a cubic, which looks generally something like that, and then a line, which generally looks something like that, and they're coming together. So at 1, these 2 things are meeting up, hopefully. That's what we're determining. So the limit of f of x as x goes to 1, and we're only looking at it from one side, so we're looking at it from the left only, which means we're moving in, going closer and closer and closer from the left. Since we're looking at it from the left hand, that means we're looking at it when usually x is less than 1, right? We're looking at it going from the left, and on the left of 1, that's less. So we're going to focus on that top function. That tells us the limit of f of x is going to give us the limit as x goes to 1 of x cubed plus 3. And as x is going to 1, that's 1 cubed plus 3, which gives us 4. Okay. Now, for part B, we're looking at it from the other side. So now we're looking at it from the right side of 1. And on the right side of 1, that's when we're greater than 1. So we'll look at that bottom function. This tells us our limit as x goes to 1 is going to be of 3x plus 1, which gives us 3 times 1 plus 1, which is also 4. This is good news, because since the left-hand side and the right-hand side are both showing us the same value, that means our limit does exist, and it is 4, because we've looked at it from both sides. Now, the last question for this one is find f of 1. Well, because f of 1 is like 1 is that point where it's like, okay, do I use the top or do I use the bottom? But we're going to use the bottom because it's greater than or equal to 1. So since it's equal to 1 at that point, that's the one we use. We're going to use that bottom. So f of 1, we're plugging 1 in for x. 3 times 1 plus 1 gives us our value of 4. And that just tells us, yes, it's defined, it goes to 4. Okay. We'll do another. F of x is 5x minus 6 if x is less than or equal to 2, and it's 2x plus 4 if x is greater than 2. Okay, so let's look at it. First, we're looking at the left-hand sum, the limit of f of x as x goes to 2 from the left. So from the left-hand side, that is when our x is less than 2. So when we take our limit, we're using 5x minus 6. So that's 5 times 2 minus 6, 10 minus 6, 4. A lot of 4s in this lecture. Okay, next, we're looking at it from the right. That's when x is greater than 2. So now we're going to look at it from the right side. Tells us our limit as x goes to 2 is going to be of 2x plus 4. That's giving us 2 times 2 plus 4, and 4 plus 4 is 8. Now this one's interesting because our left-hand side and our right-hand side are not going to the same place. So when we go to find the entire limit, the limit of f of x, since one of our left-hand side went to 4 and our right-hand side went to 8, our function isn't lining up. It's not going to the same place at that point. So since our left-hand side and our right-hand side are not going to the same point, our limit does not exist. Does not exist. And then to find our value, f of 2, that's where we're just plugging it in. So we go back and look which one is equal to 2. Well, it's this one. It's less than or equal to, so that's the one we use. So we have 5, plug in 2, minus 6, which gives us a value of 4. So f of 2 has a value of 4. And that just tells us that when we have that open circle, closed circle thing going on, because it's going to give us 5x plus 6, or 5x minus 6, and then 2x plus 4. So there are two lines. One just isn't lining up to the other. We'll have a closed circle on one where it's like, okay, we're including that one, and an open circle on that one. So that way there's not two outputs. Okay, number 11. Let f of x equal x squared minus 8x plus 7 over x minus 1. Let's find some limits using this guy. So the limit of f of x as x goes to 1, let's do the dumb thing and substitute in a value of 1. So we have 1 squared minus 8 times 1 plus 7 over 1 minus 1. And we can see right away, okay, 1 minus 1 gives me, who cares what's happening on top, 0 on bottom. So that's why my professor called it do the dumb thing, because it might result in something dumb. Like it will give us a 0 in our denominator, and we definitely don't want that. So why don't we try simplifying our problem first to see if we can kind of work around this problem that's popping up. Our numerator, x squared minus 8x plus 7. This is factorable. So if we factor it, we'll get 7 and 1. And we want a -8, so -7 minus 1. So if we rewrite this, on the top, I'll have x minus 7, x minus 1. On the bottom, I'll have x minus 1. And now I have something I can cancel out. X minus 1s I can cancel, which leaves me with x minus 7. Okay. I just have to keep in mind that x is not allowed to equal 1 because that's what we canceled out. Now if I take the limit of this one, so we wanted the limit as x goes to 1 of x minus 7, which is going to give us 1 minus 7, which is -6. So now we found a value and life is good. Now let's examine what's happening from each side. So, limit of f of x as x goes to -1. So we looked at +1, we're going to look at -1. Note that it's not the left-hand side, it's actually the value of -1. We've got -1 squared minus 8 times -1 plus 7, denominator, -1 minus 1. So this is going to simplify if we do our multiplications and our additions and subtractions. 16 over -2, and that's going to simplify to -8. So at 1, our value is going to, our limit's going to -6. At -1, our limit is going to -8. Let's look at -5. As it goes to -5, what will we have? -5 squared minus 8 times -5 plus 7, denominator, -5 minus 1. We'll have 72 over -6, reducing to -12. All right. And our last example for this one, for this section, f of x is the absolute value of x minus 2 over x minus 2. And we're just going to explore the limits. We'll look at the limit going to 2 from the left, going to 2 from the right, and then does it exist? So let's start by going to on the left-hand side. So as x approaches 2 from the left, the numerator is going to be positive because it's an absolute value. Okay, we're looking at it from values that are less than 2, and then after we do our subtraction and take the absolute value, we're going to have positive numbers, but the denominator doesn't have that same absolute value. So our denominator, when we have values less than 2, after we do our subtraction, then our denominator will be negative because our x values are smaller than 2. So what we're going to have here is a limit that is going to have a value of -1 because we're plugging the same value in on the top and the bottom, but our top is positive and our denominator is negative. They have opposite signs. Next, we're going to look at it from the right. So if we're going to 2 from the right, now we're looking at values that are greater than 2. So our numerator It's going to be positive. It has that absolute value sign on it. Our denominator is also going to have positive because it has values greater than 2. If we take a bigger number than 2 and subtract 2 from it, we're going to still have a positive number. And since we're plugging the same value in on the numerator and the denominator, when we divide them, it'll just give us a 1. Since they're both positive, it'll be a positive 1. Okay, now the important part. Our left-hand side and our right-hand side are not going to the same value, so the limit does not exist. Unfortunately. Whenever we want to determine if the limit exists, we need to make sure that our left-hand side and our right-hand side are taking us to the same value. In this case, they're not. One's a -1, one's a +1. And that's it for today. This is section 2.1.